This video and this part of the course concentrate on a matrix known as the manipulator Jacobian. What is it? Well, basically this matrix is the core of an approach to talking about velocities of the robot as opposed to the positions we've talked about so far. Up to this point, basically we can think about kinematics as being looking at the robot and imaging it, taking still pictures, if you like, of it in different poses and different configurations. The idea of the Jacobian and looking at the velocity level is more like the idea of now expanding that and taking video of the robot. So now we're seeing the robot move and we're able to understand it in a different way. Why is that useful? Well, it turns out that one thing we can do with the Jacobian is to basically do an end run around the inverse kinematics problems that we looked at in the last video. So many of the issues that we saw that made robots difficult to analyze from the inverse kinematics point of view go away, or at least become easier, when we look at the velocity level. So the Jacobian is going to get us out of the hole that we dug for ourselves, in the sense that we did not have a systematic way to define inverse kinematics at the position level. At the velocity level, we'll be able to do it. The Jacobian is also useful in a number of other areas. It turns out that for just about everything we'll talk about in the class, the Jacobian turns out to be the key element to analyze it, and we'll see how. So in many ways, if the forward kinematics based upon Denevit-Hartenberg is the foundation for everything we're doing in the course, it turns out that the Jacobian matrix is sort of the glue that ties just about everything else together. So what we're going to do is very fundamental and very useful. As we will see, the Jacobian is very effective in solving the inverse kinematics problem over trajectories of the hand. In other words, creating the configuration or the shape of the robot to let the hand do what you want for conventional robots. But it's also effective for unconventional robots like this. This is a continuum or snake-like robot manipulator built by ECE Robotics. And so here the robot is taking its end effector through the logo of the company, and creating the right shape of the robot to make that happen is fairly complicated. But it's done effectively here using the Jacobian. Here's a more practical application scenario for a continuum arm, again from ECE Robotics. This is a simulation of their arm that we'll see running in a moment. So here the application is vehicle inspection. For example, at a checkpoint, you might want to look inside a vehicle to see if there are, for example, explosives underneath the seat. It's a difficult application to get into because it's hard to get in and around all the various things that are in the vehicle. And so one thing that you would like to be able to do is to take an arm in and avoid people having to do this. And so if we see the simulation run again, this is a Jacobian-driven simulation, the Jacobian built on top of Denevit-Hartenberg model for the kinematics. And so we can see again the sorts of things that these snake-like robots ought to do. So the Jacobian method that we're going to look at here in this video is applicable to lots of different scenarios. We will look at it specifically for industrial robot arms, but it's applicable across a much wider range. So what is this mysterious manipulator Jacobian that's going to prove so useful to us? Well, in terms of the way we use it, what we'll use it for is to relate movements inside the robot to movements at the end of the robot, or more formally to relate velocities q dot to velocities x dot, where q and x again are being thought of as the joint variables and the end effector coordinates. So, more specifically, the relationship once we're done is that the Jacobian will appear in this relationship here. So this is an m by n matrix in general, where there are m coordinates for x and n coordinates for q, i.e. n joints in the robot. And what it does is it basically pre-multiplies the joint velocities to give the end effector velocities. So you can think of it as filtering the movements of the joints to tell you where the hand is going to move as a result of those movements within the robot.